Hi there, this is a video showing how you might analyze the video experiment shown here at this website. It involves a bag of flour that swings down like a pendulum and hits a tissue box, and the tissue box kind of scoots forward. Your job is to figure out the coefficient of friction between the tissue box and the table a few different ways with with the information shown in the video. If you haven't watched this video and tried to figure it out on your own, you should do that first because this video that you're watching now, spoiler alert, shows you how to solve the problem. So you should try to figure it out on your own. But if you're stuck, um, this video shows how you might use a few different representations to solve this problem. So if we start with just the information we can measure in the video, we can measure the change in the height of the bag as it swings down, and then we can measure the distance that the tissue box travels after it's been smacked with the bag. The first step in analyzing this situation is to split it up into like useful moments, useful like pieces, because we need to take it step by step to get from these two measurements that we can make to what we actually want to calculate, which is the coefficient of friction. So I've identified four moments here, like right before the bag is dropped, right before the bag hits the tissue box, right after the collision between the bag and the box, and after the box comes to rest. We're going to want to analyze each of these moments sort of separately. Each of these transitions separately, and we want to think carefully about what system is going to be useful for analyzing each part. So for example, for analyzing the transition from A to B, we want to use the fact that energy is conserved from energy stored in gravitational form in this moment to energy stored in kinetic form at this moment. Again, this is before the collision with the tissue box, so we're not going to worry about energy dissipating in that collision, but we are going to draw a bar chart where we define our system to include the bag and the earth so that we can use the conservation of energy. We don't want to think about work being done because we don't particularly care about the forces involved, and the actual displacement is more complicated than just this change in height. So our bar chart is pretty simple. We're going to start with some gravitational energy, and all of that energy is going to convert or transfer to kinetic energy. The algebraic relationships for these two quantities are fairly straightforward. And if you work this out with the algebra, you end up with a velocity, or I ended up with the measurements I made of a velocity of approximately 3.7 meters per second. Again, the cool thing about these videos is you're making the measurements yourself, so you might get a value that's not precisely 3.7 meters per second and still could be right. So if you get something radically different, you want to go back and check your work, but if you get something that's approximately the same as the value that I've gotten, then you should go forward with your value because it's maybe better than the value that I calculated. So then we want to use this value going forward to analyze the transition from moment B to moment C. The problem here is that we can't use conservation of energy for this transition, for this collision, because we don't actually know and have no way of knowing the energy that was dissipated from moment B to moment C in that collision. However, we do know that momentum is conserved, and if we define our system carefully, we can use the fact that the momentum is constant from before to after. That is, like if we consider all the objects that we're concerned with in that collision, that is the bag and the box, we can use the fact that the momentum of the bag before that collision is equal to the momentum after the collision of the entire system, which is going to include the bag and the box. So again, the bar chart in this case is pretty simple. We've got momentum before, pointed in this direction, and momentum after, pointed in this direction. I've defined, well, I'm analyzing the situation assuming that the bag and the box kind of travel together after the collision. This may not be precisely true, but it's an assumption that's good enough that I feel comfortable working with it. And all I'm saying here is that the initial momentum, which is just the mass of the bag times the initial velocity of the bag, is equal to the final momentum, which is the mass of the bag plus the mass of the box moving together at some final velocity. I made this bar wide just to show that it's actually the bag and the box moving together. But essentially all I'm doing with this bar chart is showing that the momentum before is equal to the momentum after. Again, if you work out this algebra, I got a velocity for the box and for the bag too, although the bag slows down in a different way than the box does. Immediately after the collision, I got the velocity of the box to be about 0.95 meters per second, or about 1 meter per second. And going forward, our last task, almost our last task, is to analyze the box slowing down from C to D, from moment C to moment D. Now, we want to use the fact that this force diagram is describing the acceleration of the box from C to D. That is, the force of the table on the block pointing perpendicular to the table, the normal force, and the force exerted by the earth on the block. These two balance out, and the only force, or the only component of force that's accelerating the block is this component of the table on block force, the friction force. So we want to, this is the value that we are ultimately interested in. We are interested in calculating the value of this friction force, but we need to use either energy or momentum to do that. Now, if we had some information about the time that it took for this box to slow down, we could solve that as an impulse problem by setting the table outside of our system. And you could actually figure this out by looking at the video and seeing how much time it takes. I'm going to do it using this value, the delta x value, so I can't do it as a momentum, as an impulse problem, but I can do it as a work problem. However, I need to define my system carefully again so that I can use the fact that the table is doing work on the box. If I define my system to include the box and the table, then the table can't do work on that system, so I can't use the fact that work is equal to the force exerted by the table in this case times the displacement. Again, the energy before the blocks before the box starts to slow down is the kinetic energy, taking into account this velocity that I've calculated here, and then the table does work on that system, on that box, to dissipate that kinetic energy, and we end up with zero kinetic energy. So I know that this initial kinetic energy is equal to the total work done. If I work this out with my algebraic relationships for kinetic energy and work, I find that this force has got to be approximately 1.6 newtons or so. Before making that calculation, you may want to check at this point that the kinetic energy that you're working with at this step is not greater than, and it is in fact less than the energy that you were starting with up here. This is important. We know this has to be true because we know that some energy dissipated in this collision. So we would be surprised if we ended up with more kinetic energy here than we had here, for example. And if you wanted to calculate the efficiency, say, of the collision between the bag and the box, you could do that by figuring out how much energy was in the system, or in this new system after that collision, and compare it to how much energy was in the system before, to calculate how much energy was lost or dissipated in that collision. So once we've done this, it's a fairly straightforward thing to calculate the coefficient of friction. we want to use the fact that the ratio of the friction force to the normal force, which we can calculate using this force diagram, is equal to the coefficient of kinetic friction. And then we can use other information in the video to check that this value is consistent. The value that I got was about 0.17, which seems like a reasonable value for a coefficient of friction. And this checked out with the video of the scale pulling the tissue box to the right. One last little puzzle here. If you solve this problem, it's possible to show that if we don't use any of the values that we measured in the video, it's possible to show that the coefficient of kinetic friction is equal to this. This is kind of an added challenge if you have already solved the problem with actual numbers. And I wanted to show you this because it lets us do some kind of extra checking to see whether we've analyzed this problem correctly. So the first thing would be to work this through with just variables, no numbers, and work this out. These little m's and big M's, by the way, the little m is the mass of the bag, and the big M is the mass of the box. These should be labeled on the diagram, but they're not. I apologize. But the last thing that I want you to think about with this video is how we can check that this solution that we've arrived at is reasonable. We already checked it. That is, like, we checked that 0.17 value for kinetic friction. We checked against the other value that we measured with other information in the video. But there are some other questions that we can ask as well. For example, do the units work out? We know that the kinetic friction is unitless, so we need to make sure that this value here is also unitless. I see something that would be measured in meters divided by something else that would be measured in meters. I see something that would be measured in kilograms divided by something else that would be measured in kilograms. So my meters and my meters cancel out, and the kilograms cancel out, and we end up with something that is indeed unitless or dimensionless. The last question to ask yourself is if the solution works for really large values or really small values of the things that we've got here. For example, if I was to increase the delta H, that is, like, if I was to increase the height or the change in height of the bag, and the delta X was to stay exactly the same, then I would expect that would require a much bigger coefficient of friction. And that's consistent with this answer here. If I increase this value and this stays the same, then this would have to be really big. Or, for example, if I increased the mass of the box and everything else stayed the same, it would make sense, according to this, that the coefficient of friction would have to be less in order for, say, the box to slide exactly the same distance. But so checking through with a solution like this, especially if you have it in a form with just the variables, to make sure that if you increase or decrease values to either very large or very small values, that you end up getting something that's consistent with what you'd expect. That's a nice way to just make sure that the answer that you've calculated, in fact, makes sense. So you may want to go back and watch the video again, watch the original video again, and make those measurements yourself. But hopefully this was helpful in showing you that, like, the difficult parts of a problem like this are all in the bar charts and the representations. If we can make a correct bar chart, either for energy or momentum, we've basically solved the problem. The algebra is not usually the tricky part. Hope this was helpful. Thanks.